Hello ctrlX fans. This is a demonstration of the ctrlX 2-channel Oversampling Digital Output Module. This module divides the EtherCAT cycle into many smaller time slices to enable precise control of the rising and falling edge of the output. When combined with the function block MB Digital Cam Switch, this module provides high-resolution Programmable Limit Switch, or PLS, functionality. It is most commonly used to trigger actuators, dispensers, or cameras at a precise position within the product cycle. This is the physical arrangement for the demonstration. We have a ctrlX Drive Plus with integrated ctrlX core. This is the EtherCAT master interface. It is connected internally to the host drive and to this ctrlX EtherCAT I/O coupler. Connected to the coupler is the Oversampling Digital Output Module we are testing, along with a standard digital output module and a standard digital input module. This white terminal here is output channel 1 of the Oversampling Output Module, and it is wired to the first input on the ctrlX drive, which by default is configured as a probe input. The probe inputs are used for high resolution capturing of position or time based on the rising or falling edge of an input. And then the blue terminals are the reference or common for 24 volts. In this case, the I/O coupler and the drive are on different 24 volt power supplies. So I have a wire connecting the 0 volts of the I/O to 0 volts for the drive so that they have a common reference potential. This is ctrlX I/O Engineering. I already have the drive connected to the EtherCAT master. Now let's scan to detect the coupler and connected I/O modules. It sees them. The only setting that we have to adjust here is whether we're going to use 1 or 2 channels and specify the depth of oversampling. So I'm going to select 1 channel with 200 times oversampling. And then we'll download that configuration. In the ctrlX Core web interface, you can see that all the devices are present and EtherCAT is in op mode. The next step is to import the newly added I/O into the data layer real-time portion of the ctrlX PLC project. Go ahead and add everything that's associated with the coupler, which is the 3 I/O modules, with the Oversampling Output Module being the first one. Here we see an array of 25 bytes, starting at byte 0 and going to byte 24. That is 200 bits in total, which matches the oversampling depth that we selected. Back in I/O Engineering, we can see that our EtherCAT cycle time is set to 2 milliseconds, or 2000 microseconds. So each bit here is going to represent 1/200th of that 2000 microsecond cycle time, which gives us 10 microseconds per time slice that we can control with these bits. So the principle of operation is that if we wanted the output to stay on continuously, we would need to turn on all 200 bits and keep them on. But the advantage of this module is that we can control exactly when the leading edge occurs within the EtherCAT cycle by turning on only a portion of these bits during the first PLC scan. For example, if we want the leading edge to occur exactly halfway through the cycle, we would turn on all the bits from bytes 12 through 24, while the bits in bytes 0 to 11 would remain off. This would be for exactly one PLC scan. Then in the next scan, we would turn on all of the bits, and they would remain on for the subsequent PLC scans until we want to turn the output off. The falling edge of the output can be controlled in the same way. If we need the falling edge to occur exactly halfway through the EtherCAT cycle, we would turn off the first 100 bits, which corresponds to bytes 0 through 11, for exactly one PLC scan, then turn off all the bits for the subsequent PLC scans. If we had activated two channels with 200 times oversampling, then we would have byte 25 through 49 corresponding to the second channel. This is just for your understanding. The digital cam switch function block will control these bits automatically based on and off positions and other settings. MB Digital Cam Switch can be found in the CXA PLC Open library, starting with version 3.2. It's under Phase Limit Switch, POUs, MB Digital Cam Switch. Here you can see a description of the function block, possible error codes, and the inputs and outputs associated with it. I've already added it to a POU called PLS and assigned inputs to it. So let's take a look at what these inputs do. First you have the enable. If this is off, then of course you don't get any PLS functionality and the output will remain off. Then you have the oversampling factor. This has to match the oversampling selection that you made for the module in the IO Engineering. Let's jump down here. This is where you point the function block to the array of output bytes that are associated with whichever channel, channel 1 or channel 2, that you're going to apply this function block to. So here I made a declaration at a starting address of QB0. And it's an array of 0 through 24 bytes. So 25 bytes in total. So even though this appears on the input side of the function block, the user does not manipulate this array of bytes. The function block writes to these automatically to control the PLS function. Here we define the switches. A switch is a set of on and off positions. So let's go ahead and go online to explore that more. So you can have multiple sets of on and off positions. Here I defined an array of 4 switch structures. And so if we look at the first one, I've already initialized the on and off positions. So we have the first on position, which I have set to 90 degrees. The last on position, or in other words, the position where the output is going to turn off. Down here we have cam switch mode. So if it's position based, then the output will turn off when the position passes the last on position. If it's time based, then it's going to stay on for the duration that you have specified here instead of turning off based on a position. If you pick both, then the output is going to turn off whichever one comes sooner, either that the position has been reached or that this duration has been elapsed. And then here you can specify whether it's going to be evaluated in the positive direction, in the negative direction, or both directions. So with this positive direction setting, it means that if the position is moving in the positive direction, in other words counting up, then the PLS will turn on at 90 and turn off at 270. But if we're going in the negative direction, so counting down, the output would not turn on during this range. But if you want it to be active in both directions, you can select that here. Or you can select that it's going to only be working in the negative direction. Let's look at track options. Here we have on and off compensation values that we can specify. These compensations, which are specified in time, are used to compensate for electrical, mechanical, or processing delays in the system. Let's say I'm using this PLS output to trigger a high-speed camera system that takes a snapshot of the printed image on a printing machine. If I observe that the printed image is shifting in one direction as the machine speed is increased, I would adjust the on compensation until the image stays fixed in the camera view over the entire speed range. For this demonstration, I found that I needed almost 6 milliseconds of on compensation to keep the captured position in the drive aligned with the on position of the PLS. And we'll take a closer look at this later in the demonstration. And here you specify the direction in which the time compensation is going to act. In other words, whether it's going to cause the output to turn on earlier or later than it would by using position alone. Hysteresis can be used to avoid having the output toggle on and off if there's jitter in the position feedback right around the on or off position. So as long as the jitter is smaller than the window you define here, the output will not toggle on and off if it happens to be hovering right around the on position. The master phase offset can be used to shift all of the switches in one direction or another. So if I had a value of 10 in here, my on position of 90 degrees would now become 100 degrees, and my off position of 270 would now become 280. And this would apply to any other switches that I had configured. And then lastly, we have the axis whose position is going to be used as the source for this PLS function. In this case, I have it configured for drive 1, which is a real axis. And it's set for rotary modulo scaling, so the position is going to go 0 to 360, 0 to 360 continuously. And it's associated with profile 1. And profile 1 is the only drive that I have in the system, which is the host drive that the ctrlX core resides in. It's critical that the function block MB digital cam switch is called from a POU that is called from a task that is synchronous to the motion and EtherCAT cycle. So here I have a task called EtherCAT, and instead of being a standard cyclic trigger, it's an external event trigger that occurs after the ctrlX motion values are calculated each cycle. This task will execute the PLS POU. If we were to run this in a standard cyclic task, even if it's a fast task, we would get inconsistent performance with the timing of the rising and falling edges of the outputs compared to the on and off positions. Okay, let's activate the PLS. I have the axis running at 10 RPM. And the on position is set for 90 degrees. In ctrlX Drive Engineering, we can see what the captured position is of the probe input. So we're capturing 90 degrees with a high resolution. I'm running this drive in simulation mode so that we get very low jitter with the position and can really see the effect of the PLS function and the ability to move the leading edge in small increments. Let's change it to 100. And now we see that reflected here. Now let's increase the speed to 100 RPM. I have the feedback velocity displayed down here. So we're still capturing almost exactly 100 degrees. Now let's go to 500 RPM. Still looking good here. Very little movement from 100 to 500 RPM. Let's go back to 10 RPM. If we look at the status of the output bytes, we can see it toggling between 255 and 0. Now let's see what happens if we remove the on compensation. For this to take effect, we have to disable and re-enable the function block. So now instead of capturing 100 degrees exactly, we're capturing 100.35 approximately. Let's go up to 100. Now it's 103.56. Now let's go to 500. Now it's shifted by almost 18 degrees. So we can see that as the velocity increases, the delay in captured position increases also. And this is why we use the on compensation to mitigate this issue. Now let's try moving the on position in small increments, which is where we really see the value of the oversampling output module. Earlier we calculated a time resolution of 10 microseconds. Well, at 500 RPM, which is our current velocity, that converts to a velocity of 3,000 degrees per second. And if we multiply 3,000 degrees per second times 10 microseconds, we get a resolution of 0.03 degrees. So let's try changing the on position to 100.03 degrees. And now we see that change reflected in the captured position. How about 100.06? Let's go the other direction. And back to 100 exactly. What happens if we try to move it in smaller increments? What you'll find is that you either see no change, or it might jump to the next increment of 0.03 degrees, or whatever the resolution happens to be in your case. So let's try 100.01. And we see no change. How about 100.02? Still no change. 100.03. And now we see the change. We can also use the Oscilloscope tool in ctrlX Drive Engineering to visualize the pulse train from the PLS output and check the correlation with the position feedback. I have the oscilloscope configured to capture the actual position value at any moment in time, the captured value when the positive edge of the probe input occurs, and the state of the probe input, 1 being on and 0 being off. I've set the on position to 200 and the off position to 300, and I've also applied off compensation in addition to on compensation because I want to consider both the rising and falling edge of the signal. If I were to leave this at 0, the falling edge will occur at a later position than I'm expecting, just like we saw with the on position when I removed the time compensation. This is what we're currently capturing for the probe value, and we can see the counter incrementing. Let's start a capture. So as mentioned, the blue is the status of the probe input, the green is the position at any moment in time, and the red is the captured value at the moment that the rising edge of the PLS is seen at the probe input. So we can see at a glance that we're getting a pulse that starts and ends consistently at the same location in every revolution of the position feedback. Let's zoom in to see more detail. If we line up the cursor with the rising edge, it's showing a position of around 200 degrees where it turns on. and around 300 degrees where it turns off. The positions are close to what we expect, but not as accurate as the probe function is capturing. Let's see why that is. Here I've zoomed in and adjusted the position of the signals so we can better see what's going on. So the point at which the probe input changes state, we're reading 200.1375 degrees. The oscilloscope is configured to capture samples at the fastest possible rate of 125 microseconds, which is equal to the position loop clock. Each one of these dots represents a sample taken at each 125 microsecond interval. If we look at the previous sample, it's 199.7625 degrees. So the oscilloscope is limited to 125 microsecond intervals, but the probe function latches the position value with an accuracy of plus minus 1 microsecond. So in reality, the rising edge occurred somewhere around here, but the oscilloscope can't show us that level of granularity. The more accurate position captured by the probe function is shown here at 200.004 degrees. And that's what we've been looking at here. In this scope capture, I changed the on position twice in increments of 0.03 degrees. And we can see it reflected in the captured position. Let's try changing the cam switch mode. I've changed the first on position back to 90 degrees, and the off position is 270, so it should be on for exactly half a revolution and off for exactly half a revolution. I've lowered the velocity to 5 RPM, so it should be on for 6 seconds and off for 6 seconds at that velocity. I've set a duration of 3 seconds, and I'm going to change the cam switch mode to time-based. And now the output stays on for only 3 seconds. If I switch to both, it still stays on for only 3 seconds because 3 seconds elapses prior to reaching 270 degrees. But if we change this to 10 seconds, now it stays on for 6 seconds because 270 degrees is reached before 10 seconds elapses. Join the ctrlX Automation community to find further information, and use the forum to post questions about the oversampling I/O and other topics. Thank you for watching.